Finding partial derivatives is not a really hard thing to do, but once we find it, what do we interpret it as? Well, suppose we have z, which is a function of x and y, which is obviously it's a surface in 3 space. So if f of ab equals some point c, then the point at ABC is on the surface of this function f of xy. So if we fix y to find the partial derivative with respect to x, that's equivalent to finding the derivative of the intersection of, this should be of, not if, of the function f of xy with the vertical plane y equals b. So likewise for the partial with respect to y, if we fix x, then that would be the vertical plane x equals b or some value. So what does that really mean? Well, let's consider this function, and then we'll take a look at some graphs. If I find the partial with respect to x is going to be equal to negative 4x, because the derivative of a constant is 0. This is a constant with respect to x, so that derivative is also 0. So all I'm left with is negative 4x. Likewise, the derivative or the partial with respect to y, both of these guys are going to be constants, so I'm going to end up with negative 9y squared. So these are the two partial derivatives. But what does all this mumbo jumbo mean up here? Well, let's go ahead and take a look at Maple for a moment here. Here's my function, and let's just go ahead and get a quick plot of it. This pound sign right here, in case you haven't seen that yet, that's a comment. So it's going to ignore what I have in that line right now. So just to display the function. Here's the function. So this is a surface. I can spin around, take a look at it from different angles and so forth. It's just, you know, a typical surface. So what happens now if I take the partial with respect to x and I'm going to fix y? So suppose I fix y to be 5. The value of y is not really relevant at this point, but I'm just fixing it at some value so we can see what's going on here. So now let's put in b so I can see both of them. And what I have, let me make this a little bit bigger so you can see it better. What I have is this surface, and this surface is intersected by this plane. Now when I look at this plane, what I can clearly see at the intersection point is some type of curved function, there's some type of curved line. Well, that's a quadratic of some type. So if I take the derivative of a quadratic, what I expect to get is something linear. And that's exactly what I have. Because in reference to x, I have a quadratic. So the partial with respect to x, once I fixed y, is in fact a linear function. On the other hand, if I change this to say x equals 5, and I take a look at the partial with respect to y, when I look at that plane, what I'm seeing here is a function that looks like a third-degree polynomial. And the derivative of a third-degree polynomial is, of course, a second-degree polynomial. Let's see if I can straighten that out a little bit. There we go. So the derivative of this should be a second-degree polynomial, which is exactly what we got. See, in reference to y, this is a third-degree polynomial because these other guys are constants over here. So when I take the derivative, I did, in fact, get a second-degree polynomial. So another way to think of this is this going to be the derivative, in this case, in the direction of y. It may be difficult to see, but right here is the y. This is a positive y-axis. So this is going to be the derivative in the direction of y. That's what the function looks like in the direction of y for a fixed value of x. Likewise, the other, let me change this back to y. The other was, see, here's the x-axis now right here. This is going to be the derivative in the direction of x for a fixed value of y.